Today we are going to be looking at spectral decomposition of matrices. We've got quite a few learning outcomes, and we are going to begin by looking at the determinant of a matrix in terms of its eigenvalues. So the determinant of a matrix is equal to the eigenvalues of the matrix multiplied together. So for a matrix A, the eigenvalues are defined using the characteristic equation, which is that A minus lambda I is equal to 0. So let's say we had some sort of n times n matrix, then the polynomial that this characteristic equation gives will have a degree of n, right? And so if we were to factorize that polynomial that we got with degree n, it would look something like this, where y1, y2, y3, all the way up to yn are the eigenvalues. Now, if we sub in lambda is equal to 0, if we look at our characteristic equation, we are just left behind with det A. And from the factorized form, so from this, we're just left behind with y1 multiplied by y2 multiplied by y3. And therefore, the determinant of our matrix A, which is an n by n matrix, is simply the eigenvalues multiplied together. Cool. If we use some numbers this time, so let's say we had the matrix 2, 4, 5, 6. The determinant of this matrix A is 12 minus 20, which is minus 8. If we write down the characteristic polynomial, we get lambda squared minus the trace, which is 8, lambda minus 8, because that's the determinant. And so we get our eigenvalues as 4 minus 2 root 6, and our second value as 4 plus 2 root 6. If we now multiply these two eigenvalues together, we do in fact get minus 8. So the determinant is always the eigenvalues multiplied together. If we now look at the trace using eigenvalues, the trace is always the sum of the eigenvalues. So the determinant is the product of the eigenvalues, the trace is the sum of the eigenvalues. So if we had some matrix A, the trace of A would be the sum of its eigenvalues. If we had the matrix A, which is going to be 4, 6, 7, 2, the trace of this matrix A is 6, so that's just us doing the elements in the diagonal added together. If we now work out the characteristic polynomial, we get this, which gives us two eigenvalues, 3 plus root 43, and then 3 minus root 43. When we add up these two eigenvalues, we can clearly see that it is 6. Cool, so the trace is always the sum of the eigenvalues. Cool, if we now move on to spectral decomposition. Spectral decomposition just writes a symmetric matrix in terms of its eigenvalues and eigenvectors. So the sort of formula for this is if we had the matrix A, it would be the sum from I is equal to 1 to n, or the number of dimensions of the matrix, and then the first eigenvalue, and then the corresponding eigenvector multiplied by the transpose of that corresponding eigenvector. Okay, so let's say we had the matrix 3, 1, 1, 3. We can clearly see that this is a symmetric matrix, and it has eigenvalues 4 and 2. And then the orthonormal eigenvectors are 1 over root 2, 1, 1, and then 1 over root 2, 1 minus 1. So orthonormal just means that its magnitude is 1 and they are both perpendicular to each other. So now if we use this formula, we start with 1, we're going up to 2, and then our first eigenvalue, and then the tensor product between the corresponding eigenvectors. So if we work this out, we get lambda 1 v1 v1 transposed plus lambda 2 v2 v2 transposed. Now if we fill this in, we get 4, and then this is the exact same as doing v1 tensor product v1, so we get 4 multiplied by 1 over root 2, 1, 1 tensor product 1 over root 2, 1, 1, and then 2 multiplied by 1 over root 2, 1 minus 1 tensored with 1 over root 2, 1 minus 1. So if I now work this out, we get 4 multiplied by a half 1, 1, 1, 1 plus 2 multiplied by a half 1 minus 1 minus 1, 1. And so we get 2, 2, 2, 2 plus 1 minus 1 minus 1, 1. And so our matrix becomes 3, 1, 1, 3. So we have reconstructed our matrix A purely from its eigenvalues and its eigenvectors. So that is what spectral decomposition is. What we can also do is express matrices using eigenvalue decomposition. So this is when we express a matrix A as Q and then an uppercase lambda and then the inverse of Q. So Q is just a matrix with columns as eigenvectors. A is a diagonal matrix with the diagonals being eigenvalues, and then Q inverse is just the inverse of the eigenvector matrix. So this is for any type of matrix. If we had a symmetric matrix now, life becomes a bit easier, where we have Q multiplied by capital lambda, but this time we times that by just the transpose of Q. So this is for symmetric matrices, and this is because we make the eigenvectors orthonormal. We make slash they are orthonormal. So if we had the matrix 3, 1, 1, 3 as before, where its eigenvalues were 4 and 2, and our eigenvectors was 1 over root 2, 1, 1, and 1 over root 2, 1 minus 1. If we used this approach, because that is for any type of matrix, we would have 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2. 4, 0, 0, 2. It's important that I put the 4 first because I use this eigenvector first. And then the inverse of this matrix is the exact same. And so if I now multiplied all of this together, I would get the matrix 3, 1, 1, 3. Now, you might be asking why we even do this. Well, we do this because spectral decomposition allows us to turn a complicated matrix into a much simpler diagonal form. So if we have A is equal to QA and then the inverse of Q, I should say capital lambda, then instead of working with the matrix A, we can just work with the diagonal matrix capital lambda because they are much easier to work with. So, for example, if we had a matrix A, which is a 3 by 3 matrix, and we wanted to work out a to the power of 5, that means we would have to do A multiplied by A, multiplied by A, multiplied by A, multiplied by A. So we'd have to do 4 full matrix multiplications, which would be quite a long thing to do. So if we use eigenvalue decomposition, then if we work out A squared, we would have A multiplied by A. If we now substitute this in, we get A squared is equal to Q lambda inverse Q and Q lambda inverse Q. And then Q inverse multiplied by Q is just the identity matrix. So we are left behind with A squared being equal to Q lambda squared and Q to the minus 1, because both of these is just the identity matrix. And so now, if we wanted to work out A cubed, we could use Q lambda squared, Q to the minus 1, multiplied by Q lambda, Q to the minus 1. Like before, these two times together to make the identity matrix, so we're left behind with Q lambda cubed, Q to the minus 1. And so this is how we'd work out A cubed, and we'll just do the same thing for A to the power 4 and then A to the power 5. And what you should start to see is that there is a pattern. When we have A to the power of K, to work that out, we'll just do Q lambda to the power of K and then the inverse of Q. And lambda to the power of K is very easy to work out because lambda is a diagonal matrix. So if this was our diagonal matrix, if we are now going to raise this to the power of K, all we need to do is raise these eigenvalues to the power of K as well, which is quite easy to do. So if we go back to our matrix A, which we've been using from before, 3, 1, 1, 3. From before, we know that our eigenvalues are 4 and 2. So that means our diagonal matrix with the eigenvalues is going to be 4, 0, 0, 2. If I'm now trying to work out A to the power 5, then I'm simply going to raise this matrix to the power 5. So we're going to get 4 to the power 5, which is 1024, and then 2 to the power 5, which is 32. And then, because this is a symmetric matrix, I will use the orthonormal eigenvectors, which were these, and when I find the inverse of this, it is just the transpose of this matrix, which happens to be the same thing. So now when I multiply these two matrices, we get that, and then multiplying these two, we get this. So this is just a much easier way than doing this matrix times by itself 5 times. Cool. If we now look at this last bit, which is calculating the inverse of a symmetric matrix using eigenvalues. If we start with our rule from before, we know that A can be written as Q capital lambda and then QT, as we're now looking at symmetric matrices, where Q is the orthonormal matrix of eigenvectors and lambda is just the diagonal matrix of eigenvalues. If we now take the inverse of A, so A inverse is equal to Q lambda QT all to the power of minus 1. And if we use the rule that if we have 3 vectors timesing together and they're all to the power of minus 1, then we can write that as C to the power of 1, B to the power of minus 1, and A to the power of minus 1. So this becomes QT to the power of minus 1, lambda to the power of minus 1, and then inverse Q. So now, because the eigenvectors are orthonormal, we know that Q minus 1 is equal to Qt, and then Qt, when we inverse that, that would just be Q. So we just get Q, our diagonal matrix, and then Qt. So this would be our final formula when we calculate the inverse of a symmetric matrix using eigenvalues. A cool trick now is that when we find the inverse of this diagonal matrix, all we need to do is just invert each of the eigenvalues. What I mean by that is we just do 1 over the eigenvalues. But this is only the case when no eigenvalue is 0. And hopefully you can see why, as we can't divide by 0. So we can only do this when no eigenvalue is 0, which is pretty much always the case for us. If I were to write this formula in this way, what we are essentially doing is just summing from I is equal to 1 all the way to however many dimensions the matrix has, 1 over the eigenvalue, and then the tensor product between the eigenvectors, which we write like that. So that's how we would calculate the inverse of a symmetric matrix using eigenvalues. So yeah, this is just something that we need to know.